Welcome. So here we go. We're going to talk about electric potential and electric potential energy. They're kind of different things, but they're related, similar to how force is related to electric field. So we basically have this idea that, let's just find the analogy. So we have this electrical force, and if we want, and that's basically between two charges, a big Q and a little q. And if we want to find the electric field at some point near the big Q, so now we have a point of interest, then we say, well, we have an electric field. And our electric field is equal to our electric force that this little charge would feel if it was there. So we say it's the force over a little test charge. But it's an abstraction, of course. It's not. You don't need two charges. You don't need this little charge to be there. You don't need a force to be there. It's just an abstraction. So the electric field emanates from all charges in all directions. It falls off, as we'll see, it's going to fall off in a inverse square law. And it is the force that you would feel per unit charge if you were there, but you're not there. We find at first, I don't know what you feel about it, but my first reaction to electric field was, who needs it? I can figure out forces. Why do I need fields? But it turns out it is kind of useful. And over on this side, we have the energy. Now I'm going to just say my energy, electrical energy, if you like. In fact, let's just make it a bit more visual. The difference in electrical energy, the difference in energy between 2 points. And how do I get that? Well, I did my diagram, didn't I? I had a charge there and I have a little charge there. And there's going to be a, energy stored in that combination, yeah? And I could say, well, that's interesting, but I want to know the amount of energy I've stored depends upon this guy. And suppose I want the generic value of, depending upon, if it was one charge there. So I'd have this and a point of interest. And I'd say, well, then I have my potential. So my potential equals my change in potential energy over a little bit of charge. So if this was 2 coulombs, it would be divided by 2. If this was 5 coulombs, it would be divided by 5, etc. So they're playing the same game. This is the brute force thing, the electric force, and this is the brute force thing, the potential energy or the change in potential energy. And this is an abstraction to some extent. This is the electric field, and this is the electric potential. We use this all the time. When you go and buy a 10-volt battery, or when you go and tune in, plug into the mains and you get 120 volts, this is what you're looking at. And it is the amount of energy per charge or per coulomb. Some new language. We talked about this a little bit before. We have the gravitational force and we had the gravitational field strength, little g basically. And then we talked about gravitational potential energy, but we didn't talk much about gravitational potential. And the gravitational potential energy is, if I have an Earth and I have a mass, how much potential energy does this mass have at that point near the Earth? And the gravitational potential would be how much energy would a 1 kilogram mass near the Earth have at that point. So it standardizes things. If you tell me the gravitational potential, so if you tell me the gravitational potential, I can plug in my own mass to get the amount of potential energy I have. Same thing goes for good old mother charge. If I want to know the electric potential, it's how much potential energy does that little charge have at that location near a point source of charge. And if you like, you can have a one Coulomb charge there. How much potential would a 1 Coulomb charge have at that point? Okay. So we didn't talk much about gravitational potential because we didn't hop from planet to planet to planet, and there was enough fish to fry already. But we will talk about electrostatic potential because, you know, we're more familiar with some of this early stuff, so we can add a little bit to the later stuff. And we do hop from charge to charge to charge center. So we've got electrostatic force measured in newtons, electrostatic field strength measured in newtons per coulomb, electrostatic potential energy measured in joules, and the electrostatic potential measured in joules per coulomb, and we call that the volt. And if I think back about my equations, I said the force due to gravity was big G, big M, little m over r squared. And if I wanted my gravitational field strength, well, let's just work this out a bit more. That would be big G, big M. The little m's cancel over r squared. Forget the unit vector. This is all right. Put the unit vector in there. It doesn't matter. But can you see how it looks somewhat similar? That's an inverse square law. That's an inverse square law. This has big M and little m. This only has big M. And if I think about gravitational potential energy, it was the integral of fx dx or fg dr, whatever you want to do. And it's going to be, well, I basically have minus g, big M, little m over r. I'm basically multiplying by an r, so that r cancels. One of those r's cancels. And you see now, big M, little m over r. Big M, little m over r squared. It's similar but different. And if I take this gravitational potential, then it's minus g, big M over r. The little m's gone and the r squared is gone. Same thing happens over here. Big Q, little q over r squared. This is going to equal Ke, big Q over r squared times r hat. And then this would be big Q, little q over r, and this would be big Q over r. So those analogies, the more you enmesh them, the better. Units. Gravitational force is in newtons, electrostatic force is in newtons. Gravitational field is in newtons per kilogram. Electrostatic field is in newtons per coulomb. Gravitational potential energy is in joules. Electrostatic potential energy is in joules. And gravitational potential is in joules per kilogram. There's no shortcut for that. Electrostatic potential is in joules per coulomb, and we call that the volt. So that's a named unit. More of the same. I'm not even going to bother with that. Oh, so well, let's have a look. What I'm saying here, not more of the same. I can visualize these things. I can turn around and say, well, you know, here's a, when I'm thinking about moving up and down, I can imagine moving up and down on a mountainside. Well, we can do the same thing for electrostatics. And we can say, here's a field map, different strengths, different heights. So if I think about my volcano and the sinkhole, and I have these contour lines that go around, then I can do the same thing for positive charges and negative charges. So I can build up these surfaces. And that's kind of what I'm trying to show here. And we can say the potential energy of a charge because of its location in an electric field. So rather than saying, yeah, here's big Q and here's your point of interest, we say, well, big Q creates an electric field. and here's my point of interest. Just, you don't have to draw this part of the diagram. Just look at the field lines. It's a bit like going to a national park and having a map which doesn't have all the mountaintops on it. It's not a big deal. They're just over there somewhere. So it's the same thing with this. You don't have to have all the charges on it. You could just have the effect of all the charges, which is the electric field. So I can say, well, here I am at this point. How much potential energy do I have? Or I could say, well, here I am at two different points. What's the difference in my potential energy? How much work do I need to do in going from there to there? Now that depends on me. That depends upon how massive I am. My daughter doesn't have to work so hard because she's small. I have to work harder. But, you know, I'm stronger and she's less strong. Forget about that. The fact is that my change in potential energy depends upon factors to do with me. And notice that although we're not talking about big Q anymore because big Q is over to one side, we still need charges. To get potential energy, you need the second charge. To get potential energy difference, we need to move the second charge. But I could talk about potential, and you don't need the second charge for potential. It's how much energy a 1 coulomb charge would have if it was there. So we don't need a charge for that. And I can talk about the potential difference, which is the difference in potential energy divided by whatever charge is making the difference. So can you see how it's not that this stuff is deliberately confusing. It's just that there's an awful lot of stuff going on. And whereas I had a few attempts to kind of like visualize this as I went through my physics training, you guys are kind of getting it all at once. And so that's the thing I worry about, is you guys, it all comes at once. And it's like, you know, oh, I never thought about the fact I don't have to see the mountaintops. I can just have my little contour map. And that's like looking at my electric field. So I think what I've tried to do in this first preamble is to keep going back to the big picture, because what I find is students get lost in the detail because it's so similar and yet it's subtly different. So again, so let's just ring the changes. I can talk about point charges, or I can talk about the fields caused by point charges. And I can talk about uniform fields caused by point charges somehow. There's a whole wall of point charges over there. There's a whole wall of point charges over there. I'll get a nice uniform field. Or I can talk about non-uniform fields. So whatever I do, I'm learning how to do it when I deal with a family of point charges or with fields. And when I'm talking about fields, I'm learning how to do it with a uniform field and a non-uniform field. So keep that in mind. But we can do things like this. We can say, well, the electric force is related to the electric field, and I get from one to the other by dividing by the little charge. And I can say the electric potential energy is related to electric potential by dividing by the little charge. Clearly, if you want to go the other way, you multiply by the charge. And electric force is related to electric potential energy by the distance the force moves through. Work equals force times distance. So multiply somehow by a distance. And if I want to go from the electric field to the electric potential, multiply by the distance. Now, if it's a non-uniform field, that multiply by the distance becomes a bit hard. You've got to integrate because the field is changing as you go, which means the force is changing as you go along the line. But we'll get to all that. Just kind of keep the big picture. And let's have a look. That's kind of saying the same thing. So two broad approaches. I can say, what's going on at this point, whether I put a charge there or not, which is in a family of other charges. Or I can say, let's create the contour lines and the field lines, these are E field lines, that are caused by these charges. It's not the right for these charges, I'm just drawing one. And let's not worry about where the charges are. And just in my mind's eye, the way I'm kind of describing it is imagine that you just took that part of the piece of paper. So imagine, let's take a real rock bottom example. So here's my field lines, agreed? And I'm interested in that point here. If I give you that piece of paper, it's sufficient to figure out what's going on. Because you don't need to see the charges when you have the field. That's because it's caused by the charges. Does that make sense? Yes. So that's the game I'm kind of playing when I go backwards and forwards between one and the other. So we can say we can consider localized charges and ask the questions about specific points in space in their vicinity. We can say, well, what's the potential energy of Q3? Let's have a look. What is the oh, I'm sorry. So now I'm saying, what's the potential energy of this guy caused by its location? I suppose I could ask that as a question. What's the potential energy difference that results from using Q3 from point A to point B? Where is point A and point B? I've not actually got it on my thing. So I could go from there to there. What's the change in potential energy? What is the electric potential at point P? Oh man, I'm sorry. I could basically ignore that bit. I could get rid of that guy and just put a point of interest there and say, what's the potential energy? What's the potential at that point? And then secondly, I can say, what's the change in potential if I move that point of interest from there to there? So for the energies, I need a charge that I am looking at. And for the potentials, I need a point that I am looking at. Yeah.
Forgive me, something is eluding me. So the potential relative to what?
The potential.
We have a point in space. So my potential is relative to what?
It is that point in space's potential. It's relative to the universe. That raises big issues. If I say my potential energy here is 500 joules, it's a fair question, relative to what? And I don't know if we did this in Physics 1, but we had this discussion about, we said that, potential energy equals mgh. Do you remember that? And we'd do things like we'd measure from the floor to the tabletop. And we say, the potential energy at the tabletop is 10 joules. But that's assuming the potential energy at the floor is 0. So that's really a potential energy difference. It's really my change in potential energy equals mgh. But then people said, well, hold on. And the thing that gets people is if you dig a hole. If I dig a hole, how can my potential here be higher when I dug a hole somewhere else? Because I'm changing my starting point. So we realize that I've got to be careful where my starting point is. And so then somebody says, well, this is straightforward. I can just go to the lowest point in the universe and call that 0 potential energy. And then everything above there will be positive. And I just measure it. Well, is it the center of the Earth? Well, no. Because the sun's lower gravitationally. Well, is it the center of the sun? No. Because the middle of the galaxy is lower gravitationally. Well, is it the center of the galaxy? No, because our galaxy is part of a galaxy group and the center of mass of that will be lower gravitationally. And I don't know where the lowest point in the universe is. This is a real problem. So you can't find the potential energy. You can find potential energy differences, but you can't find the potential energy. And then along came somebody who's really smart. And they said, I might not know where the bottom of the universe is, but I sure as heck know where the top of the universe is. All I have to do is go higher and higher and higher from any mass until I don't feel the pull of gravity anymore from anything. We might say interstellar space. And when there's no pull of gravity on me, moving me does not require any work. Does that make sense? Yeah. If there's no force on me, you can just move me, and it's free motion. It's like, well, that's relatively easy to find. And so rather than starting from some bottom that I can't find and counting upwards, what we do is we go to the top of the universe and we call that 0, and we start counting downwards. So our tabletop might actually have a value of minus 5,263 joules. And the floor might have a thing of 5,268 joules. And the difference equals 5 joules. And it's 5 joules going upwards. So we have this ironic thing where we give points in space negative potential energy. And it seems really uncomfortable, because how can you have negative scalar? You know, it's like, this is a bit frightening. But it's just a number scale. It's just a number scale. And so it works. And the same thing goes with electrostatics. I don't know where the lowest point in the electrostatic field is, but I do know that if I go sufficiently far enough away from all the charges that I don't feel any force on me, then I'm at the top of the universe as far as the electrostatic forces. I do the same game. So that electric potential is relative to, you know, the universe kind of thing. Good question. So I can do that with point charges, but then I can just try and say, oh, well, what's the potential of Q3 at some point in this thing? Oh, what's the potential energy difference when I move this thing from one point to another? Oh, what's the electric potential at that point? Oh, what's the potential difference if I go from there to there? So I do the same games. I don't actually see the charges, I just see the electric fields. So 2 approaches. Let me have a look. So basically what this is saying, forget that, I don't care about that, but what this is saying is that we're just linking this. 1 volt equals 1 joule per coulomb. And what we get is 1 Newton per Coulomb field equals 1 volt per meter. They're equal to each other. We've done that before. I'm going to jump off here and go here. Do you have the same notes as me, or have I?
Slightly different, sir.
Are they wildly different or just slightly?
There are slides that are missing.
Yeah, I haven't seen a single slide.
So I got slides that you don't have, or you got slides that I don't have?
I have slides you don't have, sir.
Okay, so we'll play with this. I'm sorry about that. It's like I put one up and I didn't think about it until I came here. Usually it's not so bad, but I think I keep changing this.
I mean, it's all the same.
Yeah, it's just the order matters and something like that. Okay, so let's start by talking about a uniform field. So I can make a uniform field by having a positive plane of charge, and then I have a negative plane of charge, like plates on a capacitor, and then my electric field looks like that. Yeah. Yep. That's a uniform field. I'm deciding, this is using the same way as the old book did anyway, which was you have your field pointing downwards. So there's my E pointing downwards. And I have a charge, little q, and I'm going to move the little charge from A to B. So we say, what's the potential differences in a uniform electric field? And I say, if the electric field is uniform, the previous equations, forget that, can be simplified. That's because the book explains them in terms of point charges, and then it goes to uniform. And I think it's easy to do uniform and then go to point charges. So consider a uniform field directed along the y-axis. So here's my field directed along the y-axis. Consider the potential difference between points A and B. Okay, so we have this equation that my change in voltage is equal to minus the integral between of E dot ds. And I need to tell you where that comes from. And so I'm going to say, let's get to it, okay? So I have a force, and the force divided by the little charge gives me the electric field. So this electric field is my joules per coulomb. And if I multiply my force times a distance, I get work done. Yeah? And work done gives me my change in potential energy. Yeah? Work done equals change in potential energy. So what I can say is, and that my change in potential energy divided by my little charge is going to equal my change in potential. So my change in potential equals my change in potential energy divided by the little charge. And my change in potential equals the work done, which equals the force multiplied by, I shouldn't say multiplied, the force times the distance times the cosine of the angle between. That's my change in potential energy divided by my little charge. And so same distance, and so that equals my force over my charge times my distance times my cosine theta, and that then equals, force over charge is E dotted with d cosine theta. Sorry, man. Of course, this isn't a dot product yet. So this is E, and we know that from work we can say force times distance times the cosine of the angle between them, or I can go force dotted with distance. So this is like E dotted with d. So let's step through that again. I have a force, and if I multiply that force times the distance the force moves through, I get my work, and that is my change in potential energy. So my change in potential energy is this force multiplied by the distance that it moves through. But it's got to be in line. Well, if it's not in line, it's the component of the distance. So we get force times d times the cosine of the angle between. Yep. And we can say that's vector force dotted with vector d. Remember that from physics 1? Remember that from physics 1? So then you just say, okay, if it's vector force times vector d, and that gives me my change in potential energy, then divide both sides by q. If my change in potential energy equals vector force dotted with vector d, then my change in potential is going to be equal my vector force dotted with my vector d over q, which equals, that's my vector E dotted with vector d. So I'm trying to show you where that E dot ds comes in. Ds is what they call in the stereotypical way is the little bit of distance. So you had a comment or question?
What's the negative sign for?
Oh, don't worry about that. Let's just get to that in the end, yeah. I'm not even there yet. But we'll get there. So the generic expression is, so now if it was a uniform field, which we're gonna actually have a uniform field, but we're gonna get there. If it was a uniform field, the force would be constant, which means the field would be constant, which means we just have to multiply, we just have to dot the E with the ds, yeah? And the way we get the D out of the ds is we integrate it between A and B. If the E is not constant, if it's a diverging field, then we have to really do the integral. We can't just multiply the two together. We've got to really do the integral. Okay? So, now, why is it a negative sign? If I rolled a boulder downhill, I get less and less potential energy. If I let a positive charge go in an electric field, it goes to less and less potential energy because the positive charge is acting like the boulder. Okay? You're rolling away from the positive charge. So, if I take that into account, what happens is when I go have a positive charge going in line with the electric field, it's going to lower and lower potentials, which means the change in potential is negative. It's going downhill. And so that's where that negative sign comes from. So, we can say, generically speaking, our change in potential is equal to the integral of E dot ds between my starting point and my ending point. Negative sign in there because of the charges, so that I get a negative sign because I'm rolling downhill for a positive charge. And what I can say is, let's work this out longhand, so that would be magnitude of E times the magnitude of ds times the cosine of the angle, but integrated, so it's like you're doing the calculation for that bit, and you're doing the calculation for that bit, and you're doing the calculation for that bit, and you're doing the calculation for that bit, you're doing the calculation for that bit, and you're doing the calculation. That's what that integral means. Add all those things up. And what we find out is, oh look, my little DS's are parallel to my E's, so my cosine theta, of course, is the cosine of 0, which is 1. So I say, oh, well, my minus the integral of E times ds. And E's constant for a constant field. E's constant. So we can take it outside the integral. And then this just becomes our path length. Our path length. And so that equals D. And so I get minus ED. For a uniform field, you don't have to be able to do all these steps. And what I've seen is people can't do it for a uniform field because they're trying to do all those steps. And the way I learned was I learned the uniform stuff and then I did the complicated stuff. So the take home that I want you to get is my change in potential equals minus E times D. For a uniform field, this is uniform. That's the take home. Now let's think about it. I have a uniform field and I'm saying what's the difference in the potential between that point there and that point there. I'm not putting a charge there. I'm just saying what's the difference in potential. It's like saying what's the difference in height between that point there and that point there. No person has to be there. It's just what's the difference in height. If I want to know what the difference in potential energy is, so I'd say my difference in my potential energy is going to equal, well, it's going to equal my change in potential. That's the energy per charge times Q. So that would equal minus QED. So I have two simple equations, and I can get one from the other. I learned delta U equals minus QED, quite easily done, they'd say, quite easily done, and you just remember it. But those two are really useful equations. I'm going to go to the next page. So burn it into your memory. Delta V is equal to minus ED for a uniform, unif. And that means that delta U equals minus QED for a uniform. Where the Q is the little charge you choose to move from there to there. Burn those in. That's the take home. Change in potential energy of a test charge moved between 2 points in an electric field. So now I'm putting a charge in. Before I didn't have a charge in, now I put charge in. And I say, well, my delta U equals Q times delta V. So this equals minus Q naught E times D. So a positive charge loses potential energy when it moves in the direction of the electric field. You're rolling downhill. The electric field does work on the positive charge when it moves in the direction of the electric field. That charge is going to speed up. It's going to go faster and faster and faster if you let it go. The positive charge will gain kinetic energy as it loses potential energy. It goes faster and faster and faster. It's just like releasing a boulder down the side of a mountainside. So I go from here to here, I go faster and faster. It's like falling down. That's why they're doing the vertical field lines. But supposing you don't go along the field line. Well, okay, so I start at A and I'm going to B and I'm dealing with potentials to begin with. So I say consider an electric field that points in a negative y direction. Consider a charge that is moved from point A to point B. So I do have a charge. Let's emphasize that. I do have a charge. But they're not on the same field line. So what I say is that my potential difference is equal to, so now my potential difference, I got to go back to the generic form for a minute. I go minus the integral of E dotted with ds. My electric field is still uniform, so it's minus E times the integral of ds. And my integral of ds, it's all these little bits of ds's joined together, is equal to s. So this would be minus E times dotted with s. I'm sorry, I missed my dot out from there. It's really still there, so it doesn't matter which way I put it. Yes. So if I have a vector E and I have a vector S, I can find my change in potential by going minus E dotted with S. Yep. Question?
Well, yes. Could you give me an example of when a charged particle would not be moving parallel to the field lines?
Oh.
The influence by them go along.
I'm not actually sure. I can give you an example where a charged particle would not move parallel to the field lines. So we're kind of like doing a thought exercise here.
Maybe if you shot a particle into an electric field.
If you shoot a charged particle into an electric field, I'll just erase that bit that you said. It's exactly right. You can fire it in. It's going to be affected by it. So I could have, in fact, shame on me. Well, we skipped it. Didn't we do the bit? We were going to do the bit where we fire the particle in from the side, and we said, isn't it just like a projectile motion? We skipped it. So that would be the example, yeah. But if you let it go, it's going to follow the field lines. Well done. So, if I want to get my change in potential energy, I just multiply it by whatever charge I have, so it would be Q naught E times S. Okay. I really want to go to here. Supposing that it moves at 90 degrees to the field line, then I get my change in potential is equal to minus E dotted with S, which equals minus the magnitude of E times the magnitude of S times the cosine of the angle between them. The cosine of 90 equals 0. So that equals 0. So on a equipotential line, which is at 90 degrees to the field line, we have no change in potential. That's where the name comes from, equipotential, like we did in class. In class, you plotted equipotential lines. In lab, you plotted equipotential lines, and then you drew, based on those equipotential lines, your field lines. Yeah? That was what you did in lab. And we just proved that there's no potential difference between 2 points on an equipotential line. Okay. Let's stop for a minute. I can't. Unfortunately, I got to jump here. I'm not saying stop, take a break. I'm saying let's stop for a minute and let me do something, because this needs to be a bit reinforced. So boom, boom, boom. Oh, is he going to do it? Boom. Give me a couple. Come on. Okay. So let's go back and do slideshow. Let's just do some. So let's say I have, now I'm just going to remind myself of my equation so I make up decent questions. I'm going to say, what did I say? I said delta V equals minus ED, and I said delta U equals minus QED. That's what I said, yeah? So let's say we have a uniform field. E is equal to 7. What would units be? What are the units for electric field? We've done it. Well, that would be one, but I was thinking more in terms of the old, which is newtons per coulomb. Yeah, joules per meter. I think in terms of newtons per coulomb. And let's say I have a point here, P1, and I have P2. And let's say that there is 3 meters between them. Then I would say my change in potential from P1 to P2 is equal to minus ED, which equals minus 7 times D, and the D is going to be 3, so that would equal minus 21 volts.
Question, so the voltage is negative but the potential is positive.
This is a change in potential. The voltage, it turns out, will be should be negative, but it's a change in potential. It means we're going down. Yep. So let me change my ink color. Let's say that this is now a 6 coulomb charge that I am going to move to there. So I say my change in potential energy is equal to Q times my change in potential, which equals Q times minus ED, and I learn it as minus QED, which equals minus 6 times 7 times 3, which equals 5 sevens are 35, 6 sevens are 42, that's 123, I think. No? Did I do it wrong?
21 times 6.
6 sevens are 4, oh, it's 126. Where's my calculator? I'm getting too old for this.
Yeah, that's it.
Okay, yeah. So, and it's a negative because we roll downhill. Let's this is so conceptually, if I climb up a ramp that is 6 meters across and 4 meters high, and I want to know the work done by my lifting force, do I multiply my lifting force by the 6 meters? Do I multiply my lifting force by the 4 meters? Do I multiply my lifting force by the square root of 4 squared plus 6 squared? Which would be that line. Think about work. Very basic, think about work. Yeah, you only care about the distance in line with the force. Yeah? And so for this, I would say, okay, delta V is equal to minus E times D, which equals minus, in this case, let's say that E equals, let's say 7 newtons per coulomb again, just for continuity, so minus 7. But my D is not going to be the long thing, it's going to be the 4. Yeah? Which equals minus 28 volts. And let's say I put a charge here now. Minus 5 times E was 7 times D is 4. 27 twos are 14, 140 joules. And it's negative because I'm going down the slope. If I went against, it would be positive, etc. Yeah?
So if the charge is at P2 going to P1, it would be positive.
So if it was at P2 going to P, it wouldn't be positive because you're going up the hill. If you had a negative charge rather than a positive charge, the sign's reverse. Yeah. And that would come in because, well, that would come in because you'd recognize the sign's reverse. It's not, you can't just substitute, you know, oh, no, it does come in. If you had a negative 5 coulombs, that would be a negative 5 negative and negative make positive. So the sign does look after itself if you put the charge in. Okay.
So that equation is saying that it's a 5 positive Coulomb charge. The second example.
This second example, I'm saying it's a 5 positive Coulomb charge. I'm putting that there.
Right.
Yeah, it's my choice. Yeah, yeah. It's not, that charge is not causing the field, of course.
Right.
The field is caused by a whole bunch of other charges around. Yeah. Okay. We could make it a little bit. Well, you can go to a next level, which is, we said that delta V, which equals minus E times D in a uniform, which is minus E dotted with D, really, isn't it? Yeah? Really is a dot product. Can we say E dot S, E dot D? So what that means is, supposing I have an E, which is E is equal to 2I plus 3J plus 4K newtons per coulomb, and I choose to send it on some wacky journey, which is at 4I plus 3J plus 2K meters, then my delta V is equal to the dot product of those. So that would be minus 4 times 2 plus 3 times 3 plus 4 times 2 again, which equals, that's my E to D, which equals minus 8 plus 9 plus 8, 16, 25, minus 25 volts. So I can do IJKs on these things. Yeah, it's very nice. It's very nice. Okay. I'm going to pause there. I'm going to stop there and we'll take a break.